A jagged hole in the bottom or a long tear in the shell will let water into your ship. Loose water that will not only flow from side to side, but rush in and out as the ship rolls or lists. We already know that free surface reduces stability at all angles of heel because of the continuously shifting weight of liquid which produces a moving center of gravity. The amount of liquid in the compartment, that is, the amount of weight, remained constant. In the case where a compartment is open to the sea, the free surface effect is also present, but in addition, the water flows either in or out with each roll, thus adding or removing weight. This creates an additional loss of stability, which is known as the free communication effect. To determine the loss in stability from a compartment open to the sea, it is necessary to evaluate both the free surface effect and the free communication effect. We can start our experiments with an intact model with solid weights in all compartments. If we heel the model over to the 5.7-degree angle, we find that GM is 3 8/10 inches. Now let's substitute a liquid for the solid weight in one compartment. The surface tends to become horizontal. We already know that the effect will be equal to the transference of a wedge from one side to the other. The GM now measures 3 7/10 inches, which means that the loss due to free surface is 1/10 of an inch. When the compartment is open to the sea, the free surface effect is also present. But in addition, more water will flow in until the level of the surface is the same as the sea. Now GM measures 1 inch, indicating a total loss of 2 8/10 inches. If the model is heeled to the other side, the water flows out of the compartment. But the loss of GM is still the same, 2 8/10 inches. We know that the loss of GM due to free surface is the same, whichever way the vessel is heeled. In this case, 1/10 of an inch. Therefore, 2 7/10 inches, the rest of the loss, must be due to the removal or addition of weight caused by free communication. In short, the GM of our intact model with solid weights was 3 8/10 inches. Then, we had a free surface in an intact compartment. G actually moved in the same direction as the transferred wedge, to here. And the loss of GM of 1/10 of an inch was due to the virtual rise of G to G sub 3. However, when the compartment was open to the sea, the GM measured only 1 inch, indicating a total loss of 2 8/10 inches. Let us see step by step what caused this greater loss of metacentric height. In the first place, when the model was inclined, the loose water shifted to retain a horizontal surface. The center of gravity moved out, and the virtual rise of G was the same as when we had the shell intact, 1/10 of an inch. But in addition to the transfer of the wedge, some more water entered the compartment. This addition of water affects the stability like the addition of any off-center weight. It causes the center of gravity of the model to move further away from the center line, to here. If we incline the model the other way, the wedge again transfers to the low side. But now some water flows out. This affects the stability like the removal of any off-center weight. Again, the center of gravity of the model shifts further away, to here. As we incline the ship to other small angles of heel, the varying amounts of added and removed water produce a different center of gravity for each inclination. If we extend the lines of gravity, they will intersect on the center line at the same point, G sub 5. Just as with free surface, this point is the virtual position of G and may be used in place of the numerous positions of the actual center of gravity. The distance from G to G sub 5 is now the virtual rise of G. Thus, the loss of GM from loose water in a compartment open to the sea is made up of 2 parts. The 1/10 of an inch virtual rise of G due to the free surface, plus 2 7/10 inches virtual rise of G due to the free communication. Both components will vary with the width and length of the compartment. In a compartment twice as long, we know that the free surface effect is twice as great. The effect of free communication is also twice as great, because the amount of added or removed water in the double-length compartment is twice as great. Next, let us increase the width of the compartment without changing the distance from its center to the center line. When we double the width, we know that the effect of free surface increases 8 times. But the effect of free communication will increase only 2 times, because the amount of water added or removed will be again only twice as great. Therefore, the free communication effect is in direct proportion to the width of the compartment, whereas the free surface effect increases as the cube of the width. The location of a compartment does not change the free surface effect. As long as the width and length are the same, the size of the wedge and the distance it moves will be the same. It is not so with the effect of free communication. Here, the water flowing in or out affects the stability as an addition or removal of an off-center weight. When a weight is added off-center, the center of gravity shifts. Were this weight added further outboard, G would shift more. With a greater weight, G shifts still further. In a similar way, when an open compartment is located outboard, both the distance from the center line and the size of the weight are increased. Therefore, the shift of G and the corresponding loss of GM are considerably greater. For example, when a compartment with free surface is located 2 inches from the center line, the loss of GM is 1/10 of an inch. When it is open to the sea, the additional loss is only 3/10 of an inch. However, if the same size compartment is located 6 inches from the center line, the additional loss becomes 2 7/10 inches. Thus, in a compartment 2 inches from the center line, the loss of GM due to the free communication effect is 3/10 of an inch. In a compartment 3 times further outboard, the loss is 9 times as great, or it increases as the square of the distance from the center line. To sum up, the loss in stability at small angles of heel from the free surface effect depends on the cube of the width of the compartment and its length, while the free communication effect varies directly as the width and length of the surface and the square of its distance from the center line. So far, we have dealt with the loss of GM, or initial stability, from a compartment open to the sea. The loss of GM due to the effect of free surface reduced somewhat the righting arms at small angles of heel, and the additional loss of GM due to the free communication effect obviously reduced the righting arms still further. But we also know that the free surface effect reduces the righting arms at every angle of heel. And since the free communication effect increases the virtual rise of G still further, the loss in each righting arm should be proportionately greater. But at some angle of heel, pocketing against the deck or overhead also occurs in a compartment open to the sea. This reduces somewhat the width of the free surface, and the loss in stability at larger angles of heel is not as great. However, the effect of pocketing never restores the original length of the righting arms. Therefore, loose water in a compartment open to the sea impairs overall stability by reducing the length of the righting arms at all angles of heel, and by shortening the range of stability. To summarize, when the shell of your ship is torn open, the stability will always be impaired by the combined effect of free surface and free communication with the sea in an off-center compartment. And, since a weight has been added, the ship will sink deeper in the water. Remember that the important factor determining the loss of stability due to the free surface effect is the width of the compartment, and that the factor determining the loss of stability due to the free communication effect is the distance of the compartment from the center line. Loose water inside your ship can be dangerous. Know what it does. Your survival may depend upon this knowledge.